All right, hey there, everyone. We are going to continue on talking about dynamics today. Today we are talking about inclines. We've kind of saved the best for last. So inclines, of course, refer to any time we've got, instead of a flat surface, we start looking at things that are maybe on a bit of a grade. So you can imagine you going down a hill on your bike, or maybe going skiing, or tobogganing down a hill, or something like that. You have a pretty good sense probably that if you sit a ball on a flat surface, that ball is probably not going to do anything exciting. And by that I mean it's not going to accelerate. And the reason it doesn't accelerate is because the net forces on it are basically just zero. So there are forces acting on it, for example, a force of gravity, but like we talked about in the previous lessons, there would be a balancing force, this normal force that would push up. And those two forces would just be equal to each other and cancel each other out. So the total net force on it is zero. If you put a ball on a ramp, pretty obviously that ball is going to accelerate. And I want you to think about that. It's going to accelerate, and it's going to accelerate down the ramp specifically. And you might have a sense that the angle of the ramp is going to have something to do with that acceleration. So the steeper the ramp, for example, the faster it's going to accelerate down that hill. So that all makes sense, but why? Well, if it's accelerating, then there must be a net force, and the net force doesn't come from some new force. It's the same forces acting on the system, but they're going to behave in a slightly different way. So let's think about this example here. Even though the force of gravity pulls straight down, if I put a ball on a ramp, gravity still pulls straight down like this. You have to remember that the normal force doesn't always work straight up. It only was straight up in this first example on the flat ground because the normal force is always perpendicular to the surface. Perpendicular to the surface. So if I have flat ground, sure, the normal force is up, but if the incline, or if the ground's on a bit of an incline, then the normal force is going to work perpendicular to the surface of the incline. Now, when I draw this, it's not immediately obvious kind of how big these two forces are, but we need to keep in mind that this ball accelerates, and it accelerates in the down the ramp direction, right? It's going to have an overall net force down the ramp. One way to visualize what's happening here is to just add up these two forces. So if I add, for example, the force of gravity here, and then I add to that my normal force is going to go here. And there's two things I want to point out. The first thing is that there's no way those two forces cancel out, right? Because since they're not directly opposite each other, there must be some leftover. And the leftover is what we call net force. So you can see right here, the net force is this little leftover bit. And what do you know? That net force works in the down the ramp direction, so that's the way we're going to accelerate. So one way to solve these problems, and one way to think about them, is to do what I just did right there, which is to just do a vector addition. Take your force of gravity, add the normal force, and then the leftover is the net force. And you could see that vector diagram as a triangle, which you could solve and find the sides. I'm going to approach it a slightly different way. I'm going to think about these inclines in terms of the components. So what I'm going to do is I'm going to think about whenever I've got say a block on a ramp, I'm going to draw the force of gravity, and just to make my life easier, I'm going to draw that vector all the way to the bottom of the ramp here, so it connects there. So there's my force of gravity. And then I know that my normal force is, again, it's perpendicular to the surface, so it's kind of off in this direction right here. And then my ramp has a certain angle to it there, call it theta. So what we're going to do is we're going to resolve the force of gravity into components. Now this might seem weird because before, when we were breaking things into components, we broke things into x and y components, and gravity is just straight down in the y. But in this case, I'm actually not interested in x and y. I'm not interested in just up and down, side to side. What I'm interested in is how fast is it going down the ramp. So I'm going to resolve the force of gravity into components that go down the ramp and into the ramp. So it looks like this. So I break my force of gravity into a component, and I say, how much do I have to go in the down the ramp direction here, so that I can turn 90 degrees and complete my force of gravity, my vector diagram there. So that's got to be a right angle. I'm going to call this component the down the ramp component. I'm going to call that FG parallel. So that those two lines there just indicate parallel. And then I'm going to call this this vector here FG perpendicular. Has like an upside down T, so that's my perpendicular. So basically I'm saying, well, how much of gravity is down the ramp, and how much of gravity is straight into the ramp. And you might be able to picture from this that as that ramp increases in angle, those two components are going to change. When the ramp is very flat, most of the gravity would be in the perpendicular direction, and then as the ramp gets steeper and steeper, more of gravity is in the parallel direction. So there's two things I hope you notice kind of from this picture right here. The first is that only the parallel component of gravity pulls down the ramp. The perpendicular component of gravity doesn't accelerate it down the ramp because it's perpendicular to the motion, so it has no effect on the acceleration. However, when we look at this right here, look at this perpendicular component, what's happening, you might notice that this perpendicular component right here is actually the exact opposite of the normal force. And because they're they're anti-parallel, they're in opposite directions, it's the perpendicular component is equal and opposite to the normal force. Okay, so this explains why all of my acceleration is down the ramp, because the normal force is being balanced out by the perpendicular component of gravity and vice versa. So one thing I'll mention here before we move on is we have to, once we resolve this vector triangle, if you will, vector diagram, we need to figure out an angle, and it can be a little bit tricky to do. This is why I suggested we kind of draw that force of gravity vector down to the bottom, the base of the triangle, because here's one thing I want you to notice is that within this system, I've got a few triangles. I've got another triangle right here, and I'll try and draw in another color. So I've got another triangle right here that I want you to picture. Okay, this triangle right there, and that's also a right angle triangle because gravity is straight down. So this must be 90 degrees like this. Since this is 90 degrees, then I've got another angle here. Maybe I'll call it alpha. Okay, and what you notice is that alpha has to be complementary with theta, which is to say that theta is just 90 minus alpha. Right? And then I've got another triangle, which is my vector diagram triangle here. And this triangle here is also a right angle. So there's a right angle there, which means this angle kind of down at the bottom of my diagram, that angle there must be theta. Okay, and you can use geometry to work out a bunch of different proofs, but just recognize that if I draw the diagram like this, with my parallel component first and then my perpendicular component, this, say bottom angle, if you will, of the triangle is going to be equal to the slope of the incline. And you can kind of picture what would happen if that incline got steeper and steeper. You could see how theta would get larger and larger. Okay, so we're just going to do a few calculations just to kind of get some practice here. And you probably wanted a bunch of practice just drawing these vector diagrams because it's a little bit weird to resolve it into perpendicular and parallel instead of x and y. So I've got an 8 kilogram block sliding down a frictionless inclined plane. What is its acceleration? And you see there it's got an angle of 35 degrees. So if I draw my forces, so there's the force of gravity, and I go parallel component and then perpendicular component. So FG parallel, FG perpendicular, and then I do need to include my normal force, which would be this way. And I'm going to try and draw that so that it's approximately equal to that component of gravity. And then based on what I was just saying before, I know that this angle here is 35 degrees, and that's a little right angle triangle. So we've got our diagram all set up, and they were looking for the acceleration. So because we're talking about forces and acceleration, no big surprise, this is going to come down to net forces, so F net. Now what is the net force in this case? Well, down the ramp, this is the way it's going to accelerate. I'm going to call that direction the winning direction, and clearly winning is FG parallel. There are no forces back up the ramp. It's frictionless, so it just slides, which means there's no loser, and this is going to equal MA. Now, I should point out that we're going to find FG parallel. You can do this all in one go. I'll do it separately the first time just so we kind of see how it comes about. Okay, so I'm going to find FG parallel. And you can see from this triangle, this vector triangle that I've got here, it's a right angle. So I could say, for example, that the sine of 35 degrees is going to equal FG parallel over FG. So just reorganizing that, I've got FG parallel equals Fg times the sine of 35 degrees. And I know that it's the force of gravity, so really this is just equal to mg sine 35. So you might kind of get a sense, might get used to that, might kind of jump to that step in future problems, but that's kind of where that comes from. So I can sub this in down here now. So I know that Fg parallel is mg sine 35. Just before I do that, I want to just do a quick thought experiment here. How much does the mass of the block affect the acceleration? If you had a 5 kilogram block and a 20 kilogram block on a same frictionless ramp, which one is going to accelerate at the greater rate? Just kind of think about that as we go. We've got the force of gravity equals mg sine 35. So this equals mg sine 35 degrees, and that equals ma. And right away we kind of get the answer to the question that I asked before. We notice that on both sides here I've got a value of m. So the mass is actually going to cancel out. And what I'm left with is the acceleration equals g times the sine of 35. And that's going to be kind of true for any frictionless incline where the accelerating force is the parallel component of gravity. So you notice that the acceleration is just g times the sine of 35. This kind of jives with what we were thinking about before, which is the steeper the ramp, the greater the acceleration. You could imagine the world's most boring ramp in the world, which would be like this, where the theta is 0 and the acceleration would be 0 because the sine of 0 is 0. And you could imagine the most exciting ramp in the world ever created, which would be like this. It'd be like a 90-degree ramp that's not even a ramp. When you try to ski down it, you would just be in free fall. So in that case, the sine of 90 is 1 and your acceleration would just be g, which means you'd be free falling. So this kind of jives with what we were saying before. So I'll plug in my value here, and I've got 9.8 times the sine of 35. And this answer ends up being right around 5.6 meters per second squared. You consider down the ramp as positive or call it down the ramp, whatever you like. Okay, so first thing we notice is that on this frictionless ramp, the mass doesn't seem to matter. The acceleration stays the same. Okay, let's look at this one. So now we want to push a block up a ramp. Try to push this block up a ramp, and the question is, well, how hard do we have to push it? Okay, so obviously in this case, we're pushing this block up a ramp like this. There's like an applied force there. And then there's a force of gravity, which is down. Okay, so Fg. And then there would be a normal force, which would be kind of like this. Okay. Now, note that we're pushing it at a constant velocity. So we're not accelerating up the ramp. We're just pushing up the ramp. You might already have the sense that in order to push a block up a ramp, you need to match not all of gravity. See, the applied force doesn't work against all of gravity. It's only working against the parallel component of gravity. So when I resolve this into my diagram here, Fg parallel and Fg perpendicular, you can see that the applied force must be equal to the parallel component of gravity. And then the perpendicular component cancels out with the normal force there. Now, I know it's a little hard to see from this picture, but as that ramp slides up, based on the other geometric proof we did, we can say that this is our 58-degree angle right there. If you're not sure, just draw the block at the top of the ramp and do the same kind of geometry, and you'll find that that's the case. So again, we're talking about forces. We're talking about a net force equation. So in this case, F net is going to equal, now I'll call the applied force the winner. So applied force minus Fg parallel, and that's going to equal ma. Now, I said before my velocity is constant, which means that the acceleration is 0, so this whole thing cancels out. And so we could just say that the applied force is going to equal the parallel component of gravity. Now, you might have just jumped to that step right off the bat, which I think is totally valid if you just recognize that the acceleration is 0. So like we saw before, I won't go through the whole proof again, but the parallel component of gravity is going to be mg sine of the angle, which in this case is 58 degrees. And so I've got the mass of the block, which is an 11 kilogram block. So 11 times 9.8 times the sine of 58 degrees. And you'll find when you put all those numbers in the calculator, that ends up being about 91 newtons. Now, important to notice that in the first example, the mass canceled out, didn't matter. In this example, it didn't. And that's because we're finding the force. Even though these blocks would have the same acceleration down a ramp, clearly the more massive the block is, the more force is required to push it up the ramp, right? That just makes intuitive sense. So one thing I want you to think about before we move on to this next question, well, you can see here it's a 15 kilogram block on an inclined ramp, and there is a coefficient of friction. So there's a coefficient of friction of 0.21. Find the acceleration. And so I want you to think about this before we start this problem. Is mass going to matter in this case? So if we throw friction into the mix, does that mean that now I have to worry about the mass of the block? Would a heavier or a lighter block accelerate faster or slower, assuming it has the same coefficient of friction? Okay, so let's draw our free body diagram. We got our force of gravity, and by now we're getting pretty good at this. We've got Fg this way. And then I've got my normal force is that way. And then now I'm assuming that this is going to accelerate. I'm assuming that the block's going to slide down the ramp. I suppose it's possible that if there's enough friction, then the block just would never move. But based on the question, I'm assuming that there's a little friction force up this way, but it's not going to be enough to prevent it from sliding down the ramp. So when I break this into components, I guess what I'm saying is my parallel component of gravity, I think, is going to be larger than friction. So Fg parallel, and then Fg perpendicular. And again, I guess this is going to be a 40-degree angle right there, and that's a 90. So let's see what we can find. We can find our acceleration using, this is getting repetitive, another net force equation. So F net equals the winner, which is Fg parallel, minus the loser, which is Ff, equals ma. Now, I've already seen that the force of gravity is going to be mg sine theta. Okay, let's do a little thinking about the force of friction. From what we learned before, force of friction is mu times Fn. Now remember, Fn is not just equal to gravity. It's not, because Fn is in this direction, and so it's equal to the perpendicular component of gravity. So Ff on an incline equals mu Fg perpendicular, which is not the whole force of gravity. Now, from this triangle here, I could do a little solution and say, okay, so I've got my cosine. Cosine of 40 degrees is going to equal Fg perpendicular over Fg. So that means that Fg perpendicular is going to equal Fg times the cosine of 40 degrees. I apologize, it's getting a little bit squished there, but we can see that Fg is just mg, so this is m times g times the cosine of 40 degrees. Okay, now we got to put this all together. This is a bit of a mess right now, but we got to put it all together. This whole thing right here, this is equal to that. Fg perpendicular is mg cosine of 40, which means my force of friction is mu mg cos 40, which is a lot. Okay, let's put this all, and I'm doing this all algebraically because I want to show you how it all comes together. So Fg parallel, I already know that Fg parallel is going to equal mg sine of 40 degrees. And what I just found out is that the force of friction is going to equal mu mg cosine 40 degrees. And this whole thing equals ma, and I'm really squished for space, but we can hopefully see that. Now that's a bit of a mess, but one thing you might notice is that there is a mass in each of the terms in that equation. And so the mass ends up canceling out again. Mass cancels out. And that might be a little bit surprising, but it turns out that even when we factor in friction, if we're sliding down a ramp, the acceleration is not impacted by the mass. The larger mass doesn't accelerate faster. So acceleration is going to equal g sine of 40 degrees minus mu g cosine of 40 degrees. Now, if this is all a lot, like if this is just a whole bunch of algebra and it's just looking like a mess, I would encourage you to just solve these things separately. Just find FG perpendicular, find that number, and then plug it in here for the force of friction. And find FG parallel and take that number and then come down to your net force equation. You don't have to do it with all of these terms like this. But this is the way I've chosen today. So 9.8 times the sine of 40 degrees minus, and my coefficient of friction is 0.21. So 0.21 times 9.8 times the cosine of 40 degrees. Whew. And if you put that all in your calculator and you don't make any mistakes, I think you should end up with about 4.7 meters per second squared. And that is our answer. All right. That was a lot, but you're done. You're done inclines, so good for you. Thanks.